Hello. So this is our video demonstration video for part 4 or homework 4, which is physical design and timing. So this assignment demonstrates the crucial link between your Verilog code and the final physical circuit on an FPGA. So the core concept of this assignment is that a circuit's maximum speed is not just determined by the logic itself, but by the physical placement of the logic and the length of the wire it is connected to. So the objectives of this homework is understand the physical design backend of the FPGA tool flow, learn how to control the placement through chip planner, understand the impact of the placement on the timing of circuit, learn how to use a batch script to configure the FPGA directly without requiring the Quartus application. So this is just the manual that we used for this homework, and then this is the IR emitter LED for communication, and then this is its physical schematic and just few concepts, and then this is the steps that we have followed for this assignment, and then we'll just get back to the compiler. So this is the project that I've created. I've named it DE1-SoC IR, and then we have few files provided with us with the e-learning. So we have just added it to the directory and then added it to the files project navigator. So if you just see, so these are all just the code that we were already provided. And this is the SDC file. We are going to also have part one's second part. So basically like part 1B, where we'll be changing the period of the clock. So basically we'll just be changing this 50 megahertz to 500 megahertz. So we'll just look at that later in the video. So for now, part 1 establishes a performance baseline. So you just compile the design and let us just start compiling, and it's going to take some time. So we just compile the design and let the Quartus software automatically place and route the circuit in the most optimal way. You then measure its resources usage. So you'll be looking at the filters, analysis, resource usage or utilization reports, and then its maximum frequency using timing analyzer, and identify its single slowest signal path, which is a critical path. You also prove that every design has a hard speed limit by showing that it fails when given an impossible timing goal. So that will be looking when we are changing the clock to 2 nanoseconds, which is 500 megahertz. So if you see, the compilation is like 32% for now. And then this is the report. So these are just the data that was collected in the compilation report. So I've filled it, and then I've also attached the screenshot of those. And then we have also looked at the maximum frequency using timing analyzer, so which turned out to be 160.57 megahertz. And then we have also taken the 5 longest critical paths from the timing analyzer, and we have also have the delay and slack for each. So the data delay and the slack, so it turned out to be like 5.952 nanoseconds for delay and then 13.772 nanoseconds for slack. And this is the part 1B which I was telling you. So this is where we'll be changing the clock period to 2 nanoseconds, which was earlier 20 nanoseconds. So the compilation is still on 51%. So it has reached 80%, 99. Yeah. So So we can look that our compilation is done. So we just dive into the fitter summary. So if you just look at this, we have the logic utilization as 183, then total number of registers fan out are 275, and IO pins which are like 241 used out of 457, which is like 53%. And then our memory blocks being 0, and then DSPs being 0, and DLLs being 0. So we can also look at these in the resource section. So again, it's the same thing which is being summarized as being given a detailed explanation on these. So if you just look at the timing analyzer, so we have just opened the timing analyzer tool. So we just click on the create timing netlist, and then we just look at the timing. So we are just, if we remember, we need 5 critical paths. So we have written 5, and then report timing. So if you look at this, the slack time is 13.772 for one of the path, and then the data delay is 5.952, and it's heading from time count 14 to transmitter time count 29, and rest of them are following through. And then for the Fmax, so we're looking at the report Fmax summary. So if you look at this, it has turned out to be 160.57 megahertz. And then again coming to this, so this is where you'll be looking at the chip planner. So we'll be able to look at the way the Quartus Prime has allocated or made the logic blocks on the chip. So if you look at this, it has basically kept all the logic blocks close to each other. So if you just see this, you'll get to know the path between each of them. So basically in the part 2 of the assignment, we'll be just moving these logic elements, like we'll be physically moving one of them at the lower left, then one of them at the top left or top right based on our convenience. So and then we'll be looking at the critical path again. So we're not gonna change anything for now. We'll just close these timing analyzers, and then we'll go to the part 2 of the part 1, which is part 1b, where we'll be changing the 20 nanoseconds period to 2 nanoseconds. So we're just saving it, and then we are again decompiling it. So if you look at this, we have again made a tabular where we have critical path, data delay, and slack. If we just observe, we have the timing slack as minus 2.4477, which means that it is coming in after the next clock tick is already occurred. So it's running on 29%. So we have also made a small conclusion or the report analysis for each. So we just look at this, the slack for all critical paths become negative. The worst case slack is minus 2.477 nanoseconds, which indicates a severe timing violation. This means the signal's travel time is much longer than the time allowed by the clock period 2 nanoseconds. and the signal arrives at its destination register over like 2.4 nanoseconds too late. Therefore, the design fails to meet the 500 megahertz timing requirement and would not function correctly at this speed. So that was the part 1B where we had to change them, and then we can see that this compilation report is almost ready, and then we're just going to look at the feature summary. So ALMs being 184 and total registers being 312, pins being the same, and then the memories, DSPs and DLLs being the same again. So then again, if you just look at the timing analyzer window, we'll just open it again for the 2 nanoseconds experiment. So if you just look at the Fmax, so it has increased to 223.36, so nearly over from 160 to 223 is around 63 megahertz. And then we'll also be looking at the timing. So again, we'll be reporting the number of parts to be 5. And then if you just see, I've also attached this screenshot in the report. And then we can just see that the data delay is like 4.217, which is pretty the same, but if you look at the slack, it's in the negative. And then again, we are just gonna close this. So coming to the part 2 of the assignment, we are gonna change this back and then recompile this. And then basically part 2 is an experiment to prove that distance equals time on a chip. You use the chip planner to intentionally override the tool's optimal placement by moving connected logic elements to opposite corners on the FPGA. So you just create very long wires because you're just placing one on the bottom left and then one on the top. So the distance is being increased. And then when you recompile, you see a dramatic increase in the critical path delay. So this basically proves the interconnect delay, which is basically the time a signal spends traveling into a wire or in a wire to its destination, and is most significant factor in modern FPGA performance. So our compilation is being on 32%. And this also makes the uh, circuit run slowly. So basically it proves that the longer wire distance directly slows down the circuit. So let us just look at the report for this. So this is the part 2 where we change it back to 29 nanoseconds, and then we also get the compilation reports, and then we also report the 5 longest critical paths. And then this is what I got when I just physically changed it randomly to 2 different locations. And then I've also attached a circuit image which for this. So I've taken one logic element and placed it here, and then one more logic element and placed it here. So if you just look at this, you can see there is a longer path between each logic elements. And then this was the earlier one, and this is a critical path screenshot that I received for my design or my rerouting of the logic elements. So the compilation report is ready, and these will be the same because we have not changed the chip planner, or we have not been to the chip planner yet. So again, we're going to click on the create timing netlist. So this creates that, and then we just want to look at this. This is the same as what we saw. So custom reports will be reporting again the 5 number of paths. So we'll just click on one of them, and then we'll look at the locate path, locate in chip planner. So if you just remember, this is what we saw earlier. So this is how the Quartus is optimizing them. So we're just going to change the mode to assignment. So we'll be able to edit them. So we'll just select one of them, and then we'll be placing at this location, and then we'll also pick one more. So we'll place it somewhere here, and then we just save it, and then before closing we just have a look at this. So if you can see, it is being highlighted, one on this and one on this side. So we just close this, then we'll also close the timing analyzer page, and then we'll be recompiling this. So in the meantime, if you just look at this, probably I've just changed the placing again. So, but I have also reported for this design the details. So, so it's being, the progress of compilation is like 32%. So the progress is 51%. So it's gonna take some time for the compilation report to be ready. You can also look at the number of registers being increased from 275 to 289. But again, IOs will remain the same, ALMs being the same, DSPs, DLLs, and memory blocks. So the compilation report is ready. So we have just looked at this. So we'll just go to the timing analyzer window, and then create timing netlist. So if you just look at the Fmax summary, it has reduced to 86.14 megahertz. And then we'll be looking at the timing report. So again, we will be looking at 5 paths. So if you just look at this, the slack is somewhere around 8.391 and data delay is around 11.011. So Both are different because I've changed to two different paths, which is very random. So these have changed. So this is the original one, which was for the regular one, which Quartus Prime optimized for its path. This is what happened once we moved it. So it's somewhere on 9.101. So at this, it's somewhere around 11, 10, and 9.331. You can see it has a huge difference in the path. And if you just want to look at the chip planner, you can just give a right click and then look at that. So if you can just see, look at these. Once we change the physical design one to here and one to there, it has got a new critical path. So the distance is as increased, so the data has to move from this part to that part and then come back. So this internally uh, increases the data delay and then also the slack times, but it's all well within the range. The design doesn't drastically fail as we saw in the part 1b where we changed the clock to 2 nanoseconds. So we'll just be closing at this, and then we would also need a SOF file that we would want to program it to the DE1-SoC board. So we'll have to change the physical logical elements that we placed back to the normal one. So we're just gonna go to the directory and then open the file and delete the changes back. So we have to run everything using the run admin or with permissions because we're changing a lot on the secured directory. So these are the changes that we could see on those. So we're just going to delete this. So this changes those back to the normal one. And then we're just going to recompile the design. And then the new updated SOF file will be used for programming the board. So again, with the e-learning doc zip file, we also have, so just look at this. So if you just look at this, this is the zip file that we had. So in this, we also add a demo batch file. So this is the Windows batch file. So this file will be used to directly program the board without using the Quartus Prime Lite application. So we have just copied these and pasted it to the directory where we have the SOF file. So this is the SOF file. So it is not the updated one. So we are just waiting on the compilation, so that once we have that, we'll be able to directly run this batch file. So in the meantime, we'll just open the command prompt, run as administrator, and then we'll also go to the directory where we have these files. So it's still running on 43%. So it's still running on 51%. So we have the compilation report, and then we're just gonna refresh this. So if we just see the SOF file is updated at 6:36, which is the current time. So we just run this, then we're just running this batch file. So if you just look at these messages, it says that the board is programmed properly. So I'll also attach a photo of the board after it is being programmed. And then this concludes the demonstration for homework 4. So this was all. Thank you.